This video is on amino acids. So the aims for this video are to first know what a Zwitter ion is, to draw amino acids in acidic conditions and basic conditions, to know what a protein and a peptide link is, and to know the importance of hydrogen bonding in proteins. So the word Zwitter ion originates from the idea that an amino acid has an acidic end and a basic end. It has a carboxylic acid group on one end and an amine on the other. So the carboxylic acid can lose a hydrogen and the amine can gain one. So an amino acid doesn't actually exist in this form. It actually exists in the form where this H group on this side disappears and it joins onto the N, which can accept it, on the other side. So what actually the amino acid exists as is the following. It has a O- on one end, and it has a nitrogen with 3 hydrogens on attached to the carbon on the other end, so that is positively charged. This is called a Zwitter ion, and is actually neutral overall because it has a positively charged and a negatively charged in, so overall that is neutral, but it essentially acts as an ionic compound, so a crystal of this would be joined with an ionic bond, so the negative end is attracted to the positive end of another molecule. What that means is that amino acids have high melting points, because essentially what you have to break to melt it is ionic bonds, and they dissolve in water. So even though they are organic molecules, they will dissolve in polar solvents, and they won't dissolve in non-polar solvents because of this property that they have a negative end and a positive end. However, in certain conditions you can force the Zwitter ion to exist in one of the different charged states. So on this side I'm going to draw the Zwitter ion's acidic conditions, and on the other side I'm going to draw it in alkaline conditions or basic conditions. In acidic conditions, there is a lot more H plus floating around, or there's lots of H plus floating around, and so what happens is that H plus attaches to the amine group, which can accept protons. So what happens is that amine group then turns into NH3 plus, with the carboxylic acid group keeping its H on its group because there's lots of H plus floating around. On the alkaline side, you can think of it as having lots of OH minus floating around. What the OH minus will do is take the hydrogen ion away from the COO minus. It won't attach the NH2, instead it'll link with this OH minus. And so what you'll make is COO minus on this side, and on the NH2 side that won't gain the proton because it has gone to the OH minus instead. So in acidic conditions it becomes protonated and it becomes positively charged, and in alkaline conditions or basic conditions it becomes negatively charged, with this end becoming negatively charged. The fact that amino acids have 2 ends, each of which can react with each other, means that they can polymerize, very much like alkenes can polymerize in addition to polymerization. Amino acids can polymerize in a process called condensation polymerization. So if we look at the 2 ends that are reactive, that's the carboxylic acid end and the amine end, these 2 ends can react together. If I just draw them out in a displayed way, or at least the carboxylic acid bit anyway. Actually, I'll draw out both bits. Just bear with me. What happens is that the OH group on the carboxylic acid joins up with the H on an amine to make water, hence condensation polymerization, and the C-double bond O joins up with the NH group. And we call that in chemistry an amide link. But because this is a biological process, it also has, in this context, another name, and that is called a peptide link. Now, if we draw these 2 molecules polymerizing, what we'll get is H2N and then C bond O at the top, H at the bottom, CH2, CH2, and then this is where it's joined, so you have C double bond O, and then NH, and then the rest of it, so C double bond OH, CH2, CH2, and then C double bond OH. And basically this can then link up again with another one of these, and you can make a huge chain. Now this would just be a chain of one single amino acid, and proteins are basically a chain of different amino acids, and depending on what the protein is, you have a different structure, a different order of amino acids. This here would be called a dipeptide, because there's just two of them linked together. If you had three of them linked together, it would be a tripeptide, and so on. But as soon as you get a structure which is used in the body, and you have lots of different amino acids joined together, then you call it a protein. So this link here, just draw around it, the C double bond O NH link is called an amide link, or in biological circles is called a peptide link. And therefore this molecule here would be called a dipeptide, because you've got two amino acids joined together. If you look at the dipeptide I drew on the previous slide here, you'll see that it has an NH group attached to a carbonyl group. Now that means that it can form hydrogen bonds, because this N will draw the electrons away from this hydrogen, which will make it slightly positively charged, give it a dipole, and then the hydrogen will be attracted towards not the lone pair on the N, but the lone pair on this O of this carbonyl group. That is very important in proteins, because basically protein, well, the activity of the protein depends on its shape. So basically the hydrogen bonds will keep them in shape. So for example, some proteins have this spiral structure, or this helical structure, and what you'll have is C double bond O's on one bit of the helix attached to NH groups on the other side, which will keep it in place. For example, a bit like this. So that keeps the shape of the protein together. If those hydrogen bonds weren't there, then the shape would not exist, and therefore the proteins wouldn't perform the function they're supposed to perform. This gives certain things certain properties. So wool, for example, is a protein fibre essentially, and what will happen is the reason why you shouldn't wash woolen clothing at high temperatures, because at high temperatures these hydrogen bonds will break, and if that happens, then the woolen clothing will lose its shape, because those hydrogen bonds won't form again once it cools back down, because if they won't be in the right conformation, this helical structure will disappear at that high temperature, and then it won't the hydrogen or the carbonyl groups and the NH groups won't be lined up enough so that it won't form this helical structure again. So hydrogen bonds basically keep the shape of the protein in the shape it's supposed to be. So let's just have a look at a couple of past paper questions on amino acids. So this question asks you to first draw the zwitterion of alanine. Now you won't be expected to know these structures, they'll always give them to you. So to draw the zwitterion of alanine, basically I'm going to take this structure and then basically transfer this H across to the amine group, the H from the carboxylic acid group across to the amine group. So the answer to A would be the following. You'd have NH3 attached to the C in the middle, and then H, and then COO, and then CH3 on bottom, and you must make sure you put your charges in, so you have a minus on the oxygen of the carboxylic acid group, and a positive charge on the nitrogen of the amine group. So that's the zwitterion of alanine, so 6A1. Then it says, draw the species formed when valine is dissolved in an alkaline solution. Now remember, alkaline solution has extra OH minus in there, which will remove, this is valine here, which will remove this H from the carboxylic acid group. So to answer that question, so I'm just trying to delete what I've drawn already. Hold on a second. So you're taking valine and alkaline solution, so that will have the following answer. So you're going to have NH2 left by itself like that, no NH2 this time, carbon, hydrogen at the top, CH, CH3, 2. Now, a common mistake in these sort of questions is to get these groups at the bottom of the top wrong, even though they're given to you in the question. So be very careful, even when you're copying this back out. Then it'll be COO minus in alkaline solution. So this is an answer to 6A2. Draw the species form when valine is dissolved in an alkaline solution. That's what you should draw, basically the negatively charged ion of valine. Then it says draw the species formed by lysine here at low pH. So again, I'll just rub out what I've drawn here. So at low pH, that means a pH of less than 7. That means it's acidic. Remember, when it's acidic, there's extra H plus in there, so you're going to be getting the amine group protonated, a protonated amine group. So you're going to have this group here protonated, but also there's another NH2 here. And what will happen at low pH, both of those will be protonated. They'll both accept a proton. So you'll get NH3 at one end, and then C, COOH, and then H at the top, and then at the bottom you have CH2, CH2, 3 like it's written, and then NH3 on the end of both of those groups will be protonated. So you've got to be careful with that. They'll often try and trick you by putting more than one amine group in there, or more than one carboxylic acid group, and you'll have to make sure that you either deprotonate both carboxylic acid groups in an alkaline solution at high pH, or protonate both amine groups at a low pH. So it's another sort of question they could ask you to draw the structure of the dipeptide. So all you've got to do here is link the carboxylic acid group with the amine group and basically draw two of these in a row. So the answer here, you'd have NH2 on one end, and then a carbon, and then just make sure you draw the two groups at top and bottom of here. And then you get your amide link, or your peptide link, depending on what you want to call it. And so remember, it's C bond O, and then NH. Remember, water's made as well, but it doesn't ask you for what else is made. It just says to draw the structure of the dipeptide. And then just draw, again, the rest of the carboxylic, of the amino acid. So there you've got two distinct bits. There's one of them. There's the other one. And that's the dipeptide. Remember, dipeptide means two of them. As for the tripeptide, you'll have to draw three of them in a row, and so on.